One of the most important forces that we're going to study in this class is gravity. So before we start solving problems using Newton's second law, it's important to understand some basic things about gravity. So the first thing to say about gravity is that it is the weakest of the four fundamental forces that we know of. These forces are gravity, electromagnetic force, the weak force responsible for radioactive decay, and the strong force which is responsible for holding the nucleus of the atom together. Now when we say that gravity is the weakest of the four fundamental forces, so to understand how weak, let's take a look at this. We have a magnet that we're using to hold a piece of metal in place. So clearly this is happening near the surface of the earth, and the piece of metal is going to experience two forces. One is the force of gravity, the other one is the force due to the magnet. We all know that using a small magnet we can hold a piece of metal in place. Now think about this. It takes only a very small magnet to overcome the force of the whole planet Earth acting on this piece of metal. See, that's how strong is the electromagnetic force compared to the gravitational force. A small magnet can defeat the force of gravity due to the whole planet. Now gravity, however, even though it's weak, it has an important advantage. Gravity is always attractive, which is related to the fact that mass is always a positive number. Any asteroid that falls to Earth, for example, would increase the mass of the Earth, but most likely it will not change the charge of the Earth, the electric charge of the Earth. And this is because this rock that is falling on the Earth probably has as many positive charges as it has negative ones. The universe most likely has a net charge of 0, which means that the matter in the universe is equally divided between positive and negative charge. But then again, the electromagnetic force is so much stronger than the gravitational force that it would take an incredibly small percentage of the atoms of the Earth to have a net charge, and the Earth would just blow itself to pieces because of the repulsion between the charges. Now Newton was the first person to realize that there was an attractive force between all objects in the universe. He called this force gravitational force, and he correctly deduced its properties. He deduced that from the effect of this force on the motion of the moon around the Earth, that the force between the Earth and the moon should depend on several factors. One is the mass of the Earth, another one is the mass of the moon, and the third important one is the distance between the Earth and the moon. In general, he deduced that if you had two masses, m1 and m2 near each other, then there will be an attractive force between those two masses. Mass 2 would attract mass 1 with the force F2 on 1, and mass 1 would attract mass 2 with the force F1 on 2. The magnitude of these forces, they are equal in magnitude, and its magnitude is equal to g m1 m2 divided by d squared. So m1, the product of the masses in the numerator, and in the denominator, the distance between the center of the masses squared. The constant g is called the gravitational constant, and it is equal to 6.67 times 10 to the minus 11 newtons meter squared over kilogram squared. So this is another way to see that the gravitational force is a very weak force, since the constant g is such a small number. Now let's talk about the gravitational force on you, a person standing on the surface of the Earth. You are at a distance equal to the radius of the Earth from the center of the Earth. You experience a force Fg, which according to Newton's universal law of gravitation is equal to g, the mass of the Earth, divided by the distance from you to the center of the Earth, which is the radius of the Earth, square times your mass. The quantity in parentheses, if you calculate it, if you input the mass of the Earth, the radius of the Earth, and g, you get 9.83 meters per second square. Then this multiplied by the mass gives you the gravitational force on your body. Now if you correct for the fact that the Earth is spinning and you're spinning with it, that therefore you have a centripetal acceleration due to the rotation of the Earth, then you can get an effective gravitational acceleration equal to 9.8. This is the number that we're going to be using in this class. So you can see that the force of gravity acting on you, we can express it as a vector with a magnitude mg, with g 9.8 meters per second square, and the direction we can say it's down, that is towards the center of the Earth. So now let's use this to figure out the acceleration of an object that is in free fall. That is the acceleration of an object when the only force acting on it is the force of gravity. We know from Newton's second law that the sum of the forces acting on the object should be equal to the mass times the acceleration. Now the only force acting on the object, if it's in free fall, it's the force of gravity. And this force, Fg, should therefore be equal to the mass times the acceleration vector. Now the direction, let's talk about the direction. The direction of the gravitational force is down, as we said before, towards the center of the Earth. So if we use coordinate axis in the usual way with the x parallel to the ground and the y perpendicular, then we can express the force of gravity as a vector of magnitude mg and direction minus j, unitary j. So we can write minus mg j hat equals the mass times the acceleration. Notice that the mass is on both sides of the equal sign, which means you can cancel it. And the result is that the acceleration of this object will be minus g in the direction j hat. So 9.8 meters per second square downwards. The important thing to realize is that the mass cancelled, and therefore the acceleration is independent of the mass. So Newton was the first one to be able to prove Galileo's hypothesis about all falling objects experiencing the same acceleration. Just to make sure that you understand this, let's compare the force, mass, and acceleration of two different objects, one small and one big. If you compare the gravitational forces on two objects, one small and one big, then clearly the gravitational force is very different. The force on the small object is smaller than the force on the bigger object. However, this does not imply that the heavier object is going to fall faster, that it's going to accelerate faster towards the ground. And the reason is that if you look at the acceleration of each one of these objects, for the small one you will take the small force, you will divide it by the small mass, and you will get its acceleration, a1. If you replace the value of the force of gravity, which is proportional to the mass, you see that there's no dependence on mass for the acceleration. The mass is cancelled, and the acceleration for the little object is simply g downwards. For the bigger object, of course, you have a bigger force, but when you divide the bigger force by a big mass, you get an acceleration that is the same as before. Again, the mass is cancelled, and you end up with an acceleration equal to g. So even though the bigger object has a bigger mass pulling it down towards the Earth, that bigger force has to accelerate a bigger mass. So the fact that free-falling objects accelerate at the same rate is a direct consequence of Newton's universal law of gravitation, which tells us that this force is proportional to the mass of the object. Notice that if you're standing on a mountain a distance h above the ground, the force of gravity acting on you might not necessarily be your mass times 9.8 meters per second squared. That's because from Newton's universal law of gravitation, we have a dependence on the distance between you and the center of the Earth. The distance would be the radius of the Earth plus the height of the mountain. So that means that the gravitational acceleration will be dependent on how high you are above the ground. But now let's see how different would that be from the acceleration on the surface of the Earth. If you replace the value of the radius of the Earth, which is 6.4 times 10 to the 6 meters, then you see that even at a height of 6,000 meters, which is 3 3/4 of a mile high, the correction to the acceleration of gravity at that height would only be 2 parts in 1,000. So this tells you that even if you are standing at the top of Mount Everest, G equals 9.8 meters per second squared is a very good approximation. If you were to bring your bathroom scale to the top of Mount Everest and you stand on it, a typical bathroom scale would not even be able to show a difference between your weight at sea level and the weight at the top of Mount Everest. So from now on, we will use G equals 9.8 meters per second squared for the acceleration of gravity, and we will use that the gravitational force is equal to the mass times G 9.8 meters per second squared.